Okay. All right, welcome back. So just a quick note, if these Wi-Fi issues persist, I will not be doing Zoom. So it just simply doesn't make sense to lose 5 minutes of every lecture to try to get myself online in a presentable form. Of the news this week, some of you might have gone to ISSCC. Did you see anything interesting there? There is quite a bit of a buzz created by one of the keynotes, this one. He has shown this stuff before. It's Artigas, Synopsys CEO, who was showing that artificial intelligence can do better than you guys. And you know, you should feel threatened very much by that claim, if it is true, if it is real. Here is something that is shown here. However, it is, you know, these plots are not exactly quite qualified. There is some starting, you know, this is trying to optimize the digital design by using machine learning in the power time space, something that we'll be exploring throughout this class. And what they've shown here is, you know, there is some starting point. We don't know exactly where the starting point came from. You know, there is a best human effort over here, and then there are different machine learning efforts trying to do better by looking at a whole bunch of data, training a whole bunch of designs, training on that, and doing ML-based placement out and beating this design by, you know, quite a bit, you know, 20% in power and this is, you know, maybe 10–20% in timing. So that is substantial. How do you feel about this? I mean, should you just run for the door and go do machine learning from now on? Yes, no? I don't think so. First, we don't know. I mean, we really haven't seen a lot of this out there. I'll offer my commentary. There was a well-publicized Nature paper last summer about automated or ML doing macro placement. We actually have that talk in Berkeley next week. I highly encourage you. I think she'll be mentioning some of that work. I don't know why this thing blinking here, but which one of these is blinking? None of these screens, and that one is. Should I try to turn it on and off? Okay. Oh well, maybe we'll stop them. The claims in that Nature paper are hard to support. I think the paper was not really reviewed by an actual designer. It was reviewed by machine learning people, and it's impressive. There is still a lot of work to do. Actually, I think machine learning has a better chance of imitating an hour designer in a near term. The design space is, say, smaller. And our design is a little more predictable. I mean, they really stick to the script that we teach in classes like you know, 240p, and follow those. Yes, there is an amount of creativity out there that the designer performs, but most of design procedures follow kind of prescribed paths because they're known. ML, I mean, this is just really annoying. Let me see if we can do something to it. ML has a good chance of replicating that. I actually had a grad student who managed to do as well as a typical grad student or better in optimizing an op-amp. Essentially outperformed a typical grad student in 240B type of a class project. So there are things to be done there, and there is quite a few of the research efforts that are happening across the country in that space. Anything else that you might have seen at ISSCC that looks, super exciting or super threatening? You're a really quiet bunch. Did anybody go to ISSCC? Did anybody listen, watch ISSCC pre-recordings? Oh, this is not going to work. No, this is camera. Is camera on? I don't. And nobody went to ISSCC? Okay, so then you just have to trust me. What they said. Okay, back to the subject matter. We have been talking about velocity saturation and velocity saturation models. How do they affect the composition of modern logic cells? We have talked about the impact of design rules in the previous lecture. In the last lecture, we spent some time on talking about how does the velocity saturation impact the sizing of stacks, and hopefully everybody has understood that by now. The big takeaway there is that if we have a transistor stack, in order to get the same resistance as we would get in an inverter for the purposes of properly sizing them and doing our logical effort kind of calculations, we have found out that a stack of 2 transistors should be upsized by a factor of 1.5. Stack of 3 should be upsized approximately by a factor of 2. Each transistor should have the double width, double its width compared to a single inverter. Okay, there are other velocity saturation models that have been used in practice. So this is a paper that was published when, so what do I do? So I try to reattach this computer. Okay, we'll continue, and hopefully this thing will stop blinking. So this is a paper that describes something that is called the alpha power law, and that I put in your required reading. It's a short paper that was published in Journal of Solid State Circuits back in 1990 when Sakurai Sensei was a visiting scholar at Berkeley. The equation that is over there is really, really simple. It says that the saturation current of a device is W over 2O times mu C ox times VGS minus VGH to the power of alpha. That alpha, this looks exactly the same as the old school square law equation, except that the power of 2 has been replaced with the power of alpha, and alpha is a number that is between 1 and 2. Wow. And this got them, I think, like on the all-time most cited list of Journal of Solid State Circuits papers, place number 7 or something like that. Why? I mean, it's that simple. I mean, it's basically move on a lot. What's the magic about this paper? I mean, it's just the power alpha is between 1 and 2. When it is velocity saturated, we said this alpha is a number that should be close to somewhere around 1.0. I want to swap these two views. So it's a number between 1 and 2. So let's step back. Hopefully this is going to keep working this way. So instead of EECS minus EECS to the power of 2, they made a model where they replaced the 2 with a number of alpha, with a letter alpha, variable alpha, and alpha is somewhere between 1 and 2. That basically reflects the fact that we said that as the device is in velocity saturation, the spacing between those curves in the IDS versus the DS space for equal BGS increments is closer to linear than for that. So by putting something alpha that is close to 1, closer to 1, kind of makes it relatively easy to fit. And that's what is done. Okay. So when we go ahead and fit it, first, the first thing that we need to understand, this is not a physical model. This is a completely empirical model. It is just a mathematical model, has nothing to do with physics. There is no mobility equation, carrier mobility equation that works with this kind of power of alpha. It is just an IV curve. Now, one thing that you'll find out if you do this, and we sometimes ask you to do that in your homeworks, is you try to find what is the best factor alpha. And you will understand that when you do that, when you do fitting to minimize the mean square error, you'll find out that that modeling error is fairly large. If you pick a physical VPH and then try to find what is alpha. And the number of alpha is going to end up in modern processes being fit to somewhere around 1.1, maybe 1.2, so very close to 1. But the fitting error, I mean, the shape of the curve is not really going to match. If you're trying to do a fit or to get a good fit, usually you would leave two variables free, VTH and alpha, and then you'll get a better fit. As a result of that, the power of alpha, the value of alpha is going to be slightly larger than 1.2, maybe 1.3 or 1.4, but also VTH is going to be greater than physical. We'll see why in the next slide. But I can do something else also. I can fit this to alpha equals to 1. And then I have a really simple equation that ID is equal to VGS minus VTH. And that's it, times some linear proportionality factor. And that's the most common equation that I'm going to use in this class. Here's the physical explanation why VTH corresponds to the modeling of the actual IV behavior is a little bit higher than physical. Physical VTH is somewhere around 0.3 volts. The one that provides a good fit up at high VGS levels corresponds to a threshold that is higher than physical. Just keep that in mind. So what is that? What is about these models that is so interesting? First, this one is so easy to reason about. It simply says that my saturation current is linearly proportional to the voltage. And I'll use that really, really frequently in this class. I've used that reasoning in 151 as well. But also keep in mind that this model makes sense only at relatively high VGS, around the nominal VGS. If you drop the VGS down here closer to the threshold, this error becomes gross, like orders of magnitude. So this is only valid up high. If you would like to have wider validity range, you need to use the alpha power law. So that model, if you get to that model, a good fit down to close to the threshold. And that's why this paper was popular. Because a lot of people use it to model the behavior of CMOS circuits in a wide range from EED near threshold to model both power and performance changes to supply voltage. It's a really simple and effective analytical model that allows us to do it. Okay. So there is a whole bunch of models that we have seen so far. The one that I'm going to use by far the most is this one that I just mentioned. That ID is linearly proportional to the VGS or VDD in this case. It's going to be good for my delay estimates around the nominal VDD. Just have to keep in mind that it is not valid at low supply voltage. The other one that I'm going to use is this one, but only for sizing standard cell flip flops and stuff like that. The other ones, this one will be used for power performance modeling. These two, this one does not belong in the digital world. It belongs to old-fashioned analog IC courses, and this one also is not going to be used here. Any questions about this? So we finally posted assignment 1. You have a week to complete it. We are posting one more new lab, and I think that's your last lab that you're going to encounter, so your project ready. And we would like to get your project proposals in today. We'll give you feedback next week, and then you're off and going. Any questions about that? Yes.
Where was that project submission?
By email to all 3 instructors. Okay. All right, we need a model for transistor leakage. Where does the leakage come from? The leakage that we care about is typically source to drain leakage. So there is a transistor source, there is the drain, there is a gate, and there is a current that leaks through the transistor when VGS is equal to 0. And VDS is greater than 0. Where does that current come from? So if in case of an N-channel device where we have a P substrate or a P body and N-type diffusions for source and drains, what's the source of that leakage current? So somebody may say, oh, well, these are reverse bias diodes that are leaking, but that current is really small. The reverse bias diodes are leaking somewhere in sub picoamp per micron range. That is essentially an amplification thing that is happening inside this device. How far apart are these drain and source, right? I mean, some small number of, maybe 20 nanometers or so. Even if we try to engineer this device in a planar world where we do these, space out source and drains and do the lateral drain extension and so on, pocket implants there, and the two things are still relatively close to each other. So what does this NPN structure remind you of? Yeah, bipolar transistor, bipolar junction transistor. To make a really good BJT, how narrow should be the base? Narrow. But physically, how narrow, for really good BJT, how narrow is the base? How thin is that base? And it's about 100 nanometers or so. This is way less than that. I mean, you have a naturally really good BJT over here. It's going to leak and amplify any charge that is in there. To make things worse, we really don't have a good control over that BJT. We cannot turn it off. I mean, what we have, its base is only capacitively controlled through a capacity divider where there is the COX and there is some other capacitance here that we'll call CDN. So you really can't directly turn off this bipolar transistor. We're only controlling it through capacity divider. So when the gate, the source voltage is non-zero, when gate voltage is higher than 0, there is some capacitive division that is reflecting itself onto the base of this transistor, and it does leak. This is a plot of how the transistor leakage looks like. It generally, in the subthreshold region, if the threshold is somewhere around here, what we have seen before at about 0.3 volts, below that, it exponentially drops. The subthreshold slope, when you look at it here, the subthreshold slope says what is the reduction in the drain to source current with respect to the change in the gate to source voltage. Generally, it is measured by how much do I need to reduce my gate to source voltage in order to cut the current by a factor of 10. Therefore, it is expressed in millivolts per decade. The decade is 10x over here. If you look at it down here, what you'll find out is some numbers here that correspond to, in this particular process, to about 70. So the subthreshold slope would be somewhere around 70 millivolts per decade. Here is another view of what is happening with the leakage. We can plot the IDS versus VDS, this time not versus VGS. And what we'll see here for particular value of VGS here, and this is some subthreshold VGS, it can be 0 if you like. For some particular value of VGS, this is supposed to be VGS. For some particular subthreshold value of VGS, you will see output curves output characteristics that look like this. I mean, they kind of resemble what you would see in a bipolar transistor, except that bipolar transistors' output characteristics are more like this, right? Remember, you have a family of curves that correspond to different base to emitter voltages and a fairly flat. There is something that is happening here that amplifies this current dramatically. In this 130 nanometer device, it makes it roughly 5x larger. In modern devices, it makes it typically 10x larger. In some cases, now closer to 100 times larger. Where does this come from? Oh, this is something that is the effect that is called drain-induced barrier lowering. Essentially, it means that this tunneling barrier between the drain and the source is supposed to be completely controlled by the gate voltage. Remember anybody ever seen this Schrodinger's equation and potential wall between the potential barrier between the drain and the source? It's supposed to be controlled entirely by the gate voltage. I can probably draw that. Let me see if I can, if this is the source region and this is the drain region, there is supposed to be a potential barrier between the two that's controlled by the gate. The amount of electrons that can tunnel to that barrier is set by Schrodinger's equation. Some of them will make it over to the potential barrier. How many of them are going to make it though? Is not set by the, if you remember, the equation is not set that much by the width of the barrier, but by the height of the barrier. And the gate to source voltage is supposed to, changing gate to source voltage will lower the barrier and make a lot more electrons go through. Eventually, you want the channel, there is no barrier, you just simply filter. Now, what is happening in a really short channel devices? The impact of drain voltage thins the barrier, and let's try to draw this. So as my drain extends into the channel down here, will thin the barrier, but also lower it, and makes it easier for the electrons to make it over to the source. So that is why we see this. This current amplification factor is proportional to how the barrier is lowered by the action from the drain side. That's it. I don't try to quantify this. When I was an undergrad, somebody made me do these calculations, and these are not pretty. I would not be able to reproduce them now, for example.
So there is a limited value to a circuit designer or trying to do this kind of a thing. So these currents, as I said, when I can't show these currents now for a modern device, but in 32 nanometers predictive technology model, which was fairly reflective of the of what was in real technology back then, we saw this in this of 10x. And 10x is a typical optimization target for a modern device. They generally want to design a device such that the Dibble factor does not increase 10 under nominal conditions, which means in some fast corners it will exceed 10. How do we model some threshold current? Well, what you'll find out here, it is a double exponential. We have exponential behavior, exponential dependence of VGS minus VGH. That's essentially our bipolar statistic that we have. You look at this equation, KT over Q squared times E to the VGS minus VGH times N KT over Q is a bipolar statistic. KT over Q is the thermal voltage and the thermal voltage, and N is the multiplicative factor that essentially reflects the capacitive divider between the gate and the body of a resistor, corresponding to some factor that is somewhere between 1.1 and 1.4. So this is our diffusion current. And what is this? That's the DDS dependence. It's another exponential. The exponential that I've just examined in the previous slide, and that's my Dibble. We generally don't memorize that equation up there. Instead, we remember this equation on the bottom. And it's relatively easy to look at it, you can write it down. It's relatively easy to remember. It basically says that the subthreshold current is proportional to the width of the device. That's logical, it's linearly proportional to the width of the device. Unit width device has the unit leakage, and then it is exponentially proportional to the EECS and VGS. So it will be 10 to the power of VGS minus VGH plus gamma VGH divided by this factor S. S is the same subthreshold slope that we have seen up here. It is essentially 2.3 times n times KT over Q. And that number is greater than 60 millivolts per decade. The best device that we can make here would have a subthreshold slope that is 60 millivolts per decade. That's what is a theoretically possible thing to do. There are other devices that manage to beat that slope, so-called tunnel FETs, but they didn't make it very far because you can have a really nice subthreshold slope, but there is no on current, and most people buy devices for the on current or the performance. Gamma over here is so-called Dibble factor. And what's the value of gamma? By design, I just mentioned it. They said the drain should not affect the current by more than 10%. So gamma
or we should not have more than 10x amplification. So gamma is supposed to be less than 0.1 for a well-designed device. And that's all that I had. There are two things that you'll find bothersome, and there are many other effects there in the devices. Drain-induced barrier lowering is what I just mentioned. The other one is gate-induced drain leakage. That is essentially the band-to-band tunneling from the drain into the body of the device if the bands are aligned accordingly. There are a few other effects that happen in these devices. You'll hear something like the PODI or poly induced leakage in FinFETs, and a few other things that are concerning designers with these very new and very advanced devices. I'll not go over that. I will, but if you are designing something, especially precision circuitry in precision analog circuitry, you'll need to understand those things extremely well. Otherwise, those all present really great opportunity for you to lose your precious charge, which is usually what you need to faithfully represent certain signal values. In quick recap, in all terms, there are many leakage paths in a planar device, and even more in a FinFET device. Some of them are located over here. We have drain to source leakage, drain to body leakage, and gate to body paths. The one that is really on the bottom down here is the PN junction. That's the base leakage. That's what was the main source of concern when I was a graduate student. We'll all, if you want to keep some kind of a charge on a capacitor, we were all worried that we're going to lose it. But by having a reverse PN leak, that leakage is really small. It's 10 to the minus 12 to 10 to minus 13 amps per micron. Weak inversion is essentially that bipolar effect of creates in here. So it goes on top of that, depending on what kind of a device you have. The effect was here, 18 millivolts per decade. It got really bad down at about, so remember I mentioned, why did the 20 nanometer planar devices get voted off the island? Because we have the subthreshold slope of about 100 millivolts per decade, and nobody wanted that. They got replaced by FinFETs that brought this back down to 60 something, 70 millivolts per decade. So the subthreshold slope, as we were scaling, went up from 60 something millivolts to 100. When it reached 100 millivolts per decade, planar devices were done. We had to switch to thin body. So now that gets multiplied by another order of magnitude, or dribble, and then when you add the string leakage, it gets even higher. So the numbers over here are totally optimistic from today's point of view. A modern device tends to leak 10, even maybe 100 nanoamps to produce 1 micron per micron width. So ion to IOP ratio can be as bad as 10 for a fast device. More typical is of the order of 100. So it is truly a dimmer, like I don't have one handy over here, but essentially that's how what the gate does. Hopefully this all made sense, and all what you need to remember is that the current subthreshold current is a double exponential. It depends on VG exponential and VGS and VDS. The second equation that says that it is proportional to 10 to the power of VGS minus VTH plus gamma VDS divided by the subthreshold slope is something
that you should memorize from this to understand where it comes from. The other things to look at are various FinFET and FinFET kind of structures. There are new weak spots that if you're designing precision circuitry or IOs or something like that, you need to familiarize yourself with. Next thing that we would like to cover are CV characteristics. Why do we care about the CV characteristics? Is because we to calculate the delay, which is going to be our next attempt, not next effort. We need to discharge that capacitor that is basically a device plus wire capacitor. Device plus wire capacitor through a transistor. This transistor, has a nonlinear IV characteristic. It happens that this capacitor is also nonlinear, so we can try to go and try to solve nonlinear dependence of IDS to EBS with nonlinear dependence of C to VBS and go that way. That would be fairly complicated. We usually try to get a little bit more intuitive interpretations of those. There are a few interesting things that I would like to point out too, that you are going to encounter, and every few years people forget about this lecture or this part of a lecture, and they get puzzled when trying to study the standard cell library, and there are certain peculiarities that I need to try to cover in next few minutes. So all capacitances in the devices are typically nonlinear. Gate capacitance has a highly nonlinear channel capacitance. Overlap capacitance, these side fringe capacitances are mostly linear. And then there is a Miller effect during switching that you have studied in 240 that multiplies the capacitance and multiplies the nonlinear effect. Diffusion capacitance is the output capacitances of the device are nonlinear. Those are essentially junctions, and wires are kind of linear. I mean, the most linear of all of them all. How does the gate capacitance depend? So let's say, take a look at a transistor. So I have a transistor here. This is my gate. This is its source, and I would like to model C GS. So what's the value of CGS versus VGS? How does it change with changes of VGS? I mean, if you've taken 240, you probably know this. Would anybody mind sharing the knowledge from 240B? Maybe even 248? So before we hit the threshold is somewhere over here. This is not a pretty VTH. Before the threshold, what is the capacitance that we see looking at the transistor? Transistor is off. There is no channel formed. So it's CX times W times cell. CX is the capacitance, gate capacitance per unit area. And you have connectivity to both source and drain sides, and say, well, we're going to split this up 1/2 each. So we'll start with 1/2 CX WL. What happens when the channel forms? what's the amount of capacitance that you have?
It redistributes because it's not.
Yeah.
Reflexive. It's like different charge models.
And something like that, or 2/3 is the number that typically says. So we have no capacitance, none of that, it only gets connected to the, stays connected to the source. There is no part that gets reflected to the drain, so it goes up to like 2/3. Okay. Finally, somebody's speaking. So if I add, if I make both N and P devices, I'm interested in the input capacitance. I would like to know what is happening with the PMOS capacitance. What is happening with, how would I overlay the PMOS capacitance here, starting with VDD? It would behave symmetrically. It would be a half of whatever it is, and then would go up like that. This is an interesting phenomenon with the gate capacitance of a CMOS gate. It's low right around the transition when VGS or VDS is switching, goes up and then goes back down. The highest load of the gate presents is the pump there. What is happening with the drain capacitance? So, we're looking now at the transistor from its drain side. And over here, I essentially see a reverse bias diode. What's the capacitance looking into the drain? So it's we are essentially, what we see there is a reverse bias diode, which means that the more reverse bias we apply to it, and that equivalent parallel plates of the diode are spreading apart. There is more of a depletion region, so the capacitance drops. So as the capacitance that goes down. Remember, if I were to go in this direction towards forward biasing the diode, it would go up because until the diode that's conducting. And what happens to the PMOS device if we add it? By looking into the drain at the output capacitance, we see both source and the drain. Well, it would look more like that. So this would be the N, and this would be the P. So it's also nonlinear, but it is the output capacitance is nonlinear, but it has the opposite type. That's a kind of a tub shape as opposed to the bump shape. There is an important effect that goes in play here. So if I plot my C in to any CMOS gate, I will see something like this. And I, on purpose, because of the sizing of the gate and so on, and on P's and so being equal and made on purpose, this value a little bit higher than that. When we time the design, we would like to know the calculated propagation delay. This propagation delay can be TP high-low or TP. So this would be a stimulus that corresponds to TP high-low. This would be a stimulus that corresponds to low-high.
right? So I would have
here, the output would go from
I'm sorry, I made a mistake. TP high, low, it goes from high to low. So therefore the input should be going from low to high and vice versa.
So in order to find out what is the time, I need to find out what is,
We said our timing is some kind of an R equivalent times C equivalent.
how do I find the equivalent capacitance that corresponds to high to low transition? What's the load capacitance over here?
Okay, so high to low transition. So there's the capacitance
Equivalent capacitance
from when this is at VDD to VDD over 2. So this is my integration range, C, high, low. And this is C, low, high.
you take a look at the standard cell library, you'll find out that capacitances that correspond to high to low and low to high transitions are not equal to each other. Why? Because of this. They are integrated nonlinear capacitances across different ranges. That's why they're different from each other. Not by a lot, but sometimes you get surprised.
Now, I would like to calculate the energy. How much does energy each of these gates consume? So this will be CV squared and switching. So what is the C? Is this C high low or C low high? So we have an offer over here that it is C low to high because that corresponds to the charge. Do you have any other opposing opinions? Do I have a better offer? That's a good one, but do you have a better offer? So Ken, that would basically mean that that would be correct if I were charging the capacitor up to the half of the value, because low to high is the capacitance that takes this capacitance that is the equivalent capacitance of charging from 0 to VDD over 2. So you want to charge it from 0 to VDD.
You like make it a piecewise kind of function.
No, it's a different capacitance. So this will be CP, a different number in the library.
You need to integrate the whole thing.
Or CE or whatever they called it. That's the capacitance that goes in power calculations. Does this make sense? Yeah, if you have a nonlinear thing, the integration range or integration bounds really matter. You get different results if you don't pay attention to that. Okay. There is a good number to remember here. And the first approximation is Cox times W times L. And there is a good number to memorize here. Traditionally, that number has been 2 femtofarads per micron. It is more now in current nodes. But traditionally for planar technologies, that number was 2 femtofarads per micron. So for minimal length device.
held extremely well because of scaling. You know, the channel length for scaling and scaling down and capacitance for increasing in each node. Those two things compensate. So the C ox times L stayed constant. Good thing to remember. Nonlinearities can cost you accuracy if you're not modeling them correctly. We're going to see that in the next lecture, how does that affect delay calculations and the entire principle of calculating delays these days. Essentially, the output characteristic, charging output transition doesn't look like that, like we nicely plotted always. So this is my TP in time. In reality, it has this kind of a shape. And for any hand analysis, it doesn't matter. But if you're trying to do accurate timing, there would be a gross error that is more than 10%, sometimes 20%,
especially in some process corners and some voltages, and this needs to be accounted for. Again, you don't have to dive into details of that, but sometimes if you're looking into something really particular that is bothering you, you want to tape out the chip, and there are some strange timing things that are happening, could be a nonlinearity somewhere that has been modeled or may not have been modeled quite right. Few notes about the delay, and I'll spend a few minutes about this, is we have talked about the nonlinear capacitance and we have linearized it. Now, we would like to find out what is the actual and Haran. We'll spend a little bit more time on that in the next lecture, but for now, we will take a look at what we did in 151 or 251A. We said it's an average of the two DC resistances at the start of the transition and at the midpoint of the transition. So this is start, this is midpoint. The way how we can average those, again, this is something non-linear, so we can try to integrate it, or we can just simply find an average. In both cases, we stuck to this value, 3/4 times VDD over ID sat, times something that has to do with the output resistance, mostly caused by the Dibble factor nowadays. Now, this 3/4 times VDD over ID sat is wrong. We would like to find what is the actual R equivalent and R equivalent P that would nicely model what fits into these equations for TP by load, that is 11.2 or 0.7 times R equivalent times CL. Let's take a look at that. So what we did here is this thing might freeze. I don't know what it wants today. No, might not freeze. I don't know. I think this computer is having too much fun. Let me pause this. Okay, so let's try to do this. So I said this will be my starting point, and this will be my midpoint of a transition, because I'm interested in figuring out how does an inverter switch and no. All right, I'll try it over here so that we can move forward. But I do need to have a pen.
It's tragic, isn't it?
Is there a pen over here? No. Oh, look at that.
All right, let's take a look at this. AD versus EVS, exactly as they plotted them over here. I have an inverter. This is not clearly visible on Zoom, but I basically reproduced the IV characteristics. So what is happening to an inverter to each of these two transistors? So let's take a look at the NMOS always. This is the NMOS transistor as it is switching, as my VGS is going from 0 to VDD, and my VDS is going from VDD to 0 and back. If my transition here is really this abrupt, the transistor would have a VDS to equal to VDD, and it would pretty much instantaneously jump to the topmost curve here that corresponds to VGS being equal to VDD. Then it would follow that curve to the midpoint. This would be our output of the average of this resistance, and that. But this never happens in a regular day. They don't really have the sharp transitions. My transitions are more like that. Right? So does that correspond to something on this point? I'm starting from this point here, but then reaching this point on the graph much later. And the current that follows the discharge of the following the top, most top situation. So my trajectory is like that. And the same for the field. What do we call on currents here? How do we find the currents that correspond to equivalent resistance? The start of the transition is somewhere down here. And the mid transition is still in deep over here. So this 3/4 ID, VD over ID, that does not make any sense. People have observed that. We're going to run out of time, unfortunately, today. And if you notice this, I mean, you could have generated at least 2 IAM papers about 20 years ago. So essentially, they found out that in order to find a real equivalent resistance or equivalent switching current, you would take an average of a current here and a current there. This one we know exactly. IH is equal to IDS, the corresponds to VDS being equal to VDT, and VDS equal to VDD over 2. And this one over here, experimentally, they found out that it is equal to VDS being equal to VDD over 2, and VDS is equal to VDD. there are a few other consequences related to that. Multiple other people have seen this, and this is something that guides device designs. They essentially have figured out that the less of a dibble we have, or the less of this output resistance for the device we have, the better the device is. Similarly, velocity enhancements for strain affect this a lot. This is essentially the reason why we have seen that the devices have better switches with velocity enhancements. So, for strain, because that, remember, boosts the linear current. This is where the linear current is. Now, this is a super complicated one. Has been asked in tests, quizzes, exams, even prelims. What's happening in the transistor stack? So when you have two transistors in a stack, do you think I have any chance here? I might. So transistor stack, two transistors here switching, and let's not stress it too much. There is a PMOS on top, so this is my NAND2. What happens to two transistors in a stack? How, when they switch, we generally say this one would be at 1, and this one would be at going from 0 to VDD. How does that correspond? What would they do on the output characteristics? The bottom transistor is, where is it? Its VGS is always the top of this. VGS equals to VDD. So what it does is climbs up a little bit to some point and then goes back down. All what it does is goes up and down. So maybe 100 or a little more. Maybe that's. What does the top device do? Well, to start with, it will see its VDS being equal to approximately VDD. But because of this drop on the bottom transistor, it will never actually climb up to the top curve. We'll go to a lower curve and circle around that. Okay. Now, for you, a particularly puzzling one will be what happens when the top one is on and the bottom one switches. Try to draw that. So I'll give you some intuition on how these stacks actually work in the devices. The bottom line over here is that in order to model this behavior, what we see is, we somehow move around. You have different contributions of different currents. So this is a drawing of what I've just done, where the bottom transistor is always resistive. It has some linear current, which is ID3 over here, which is what half of that linear range. So this is some value ID times 3 over 1 volt. And then, that point will be 0.05 times VDD. And then the other two currents are the currents that we had before. This is a model projected to calculate the equivalent current for an inverter. which is essentially a composition of I, H, and I load. And then we have different compositions for scan, tools, and then trace. I'm out of time, and I was supposed to blast through the standard cells, but I'll have to blast through them next time. Because we've seen most of the standard cells, I wanted to add a few more highlights that are related to the current standard cell design. So we'll pick it up from here, and I may have to change the device that I'm using for scribbling on this. All right.